So let's take a look at this order thermometer a little bit more deeply. So far, we've explored on this order thermometer series that have polynomial growth, so our P series are all here, middle. We've explored series with exponential growth, those are the geometric series. And we've talked a little bit about logarithmic series over here in this category. And the dividing line, the line of demarcation between those sequences whose infinite series converge or diverge, is that dividing line that we see right here at 1 over n. That everything 1 over n and slower, everything with which every sequence which approaches 0 at a lower order than 1 over n diverges. So the divergent sequence, the divergent series are all over on this side of the line. And likewise, those series whose terms approach 0 at a order at least as high as, say, 1 over n squared will be convergent. But there's another way to kind of see what's going on in this order thermometer based on what tests are going to be the most useful in determining whether these series converge or diverge. And that is, let's think about what the ratio test is going to tell us for series that belong in each of these different regimes. So first of all, the ratio test is especially a test that tells us where a series belongs in this block right here. So the ratio test will tell us, does a series belong here? Does it belong in the category where all the geometric series are in this order thermometer? Because if it does, then we get a ratio between 0 and 1 that's going to give us a conclusion that our series is in fact convergent, if it belongs in that category. But what we're going to find out is that the ratio can also be, for a convergent series, 1. But it could also be 1 for a divergent series. So there are some series where the ratio test is going to come back with an answer that doesn't give us any useful conclusion. And the inconclusive ratio tests are those for which the ratio is equal to 1. Because when the ratio is equal to 1, that means that our series is not quite, our sequence is not quite approaching 0 at a geometric speed. And that's going to mean that we are somewhere to the left of that line which divides the polynomial series from the exponential series. And as I hope this illustrates, those series where rho is equal to 1, where the asymptotic ratio is equal to 1, some of them converge and some of them diverge. Which is why rho equals 1 doesn't tell us anything. It just tells us that our series, our sequence, if you like, lies to the left of that green line right there. But because some of the series to the left of that green line converge and some diverge, the ratio test is inconclusive for those series. In fact, we might say that when the ratio test comes back 1, it tells us that our series has polynomial, our sequence rather, has polynomial approach to 0, or maybe exponential, sorry, logarithmic approach to 0. But some polynomial series converge and some do not. So the ratio test doesn't tell us anything in that example. However, we also have a new piece on the order thermometer, a piece up at the far right. That's a piece we haven't explored yet with too much detail. But in this regime, up here, the asymptotic ratio is going to be 0. In other words, these series, these sequences, let's say, the terms are approaching 0 so fast, it's faster than any geometric series. Faster than geometric. So these are the sequences where your terms go to 0 so fast that if we treat them like geometric series, the asymptotic ratio of those geometric series is 0. And so they're really going quickly to 0. And therefore, they are certainly going to converge. And there are two different flavors. There are the factorial series, things that look like 1 over n factorial. And then there are what I call the superpowers, 1 over n to the power n. And each of these flavors of series, the terms go to 0 so quickly that it's faster than any geometric sequence does. And since geometric series whose terms go to 0 converge, that means that factorial and superpower series will also converge. So let's look at an example before we break into groups today of how we would use the ratio test to analyze a series that looks like a factorial. All right, so here's a happy series. Here the terms are 4 to the n over n factorial. And when we look at the behavior of the terms of this series, we see that they actually start by increasing before they eventually change their mind and start decreasing to 0. And again, anytime we're talking about sequences and series, it's only the eventually that matters. In fact, if I decide I want to see more terms, we'll see that this pattern, in fact, continues. That my terms, in fact, eventually, once they decide to decrease to 0, they decrease to 0 pretty quickly. So again, we want to answer the question, how geometric is this series? If we were to treat this sequence like it were a sequence which was geometric, then what would the common ratio of that geometric series be? So the first guess is 4. Because we have that 4 factor upstairs that makes it look like, well, this might actually be a geometric series because of that 4 to the n, or it might actually be asymptotically geometric because of that 4 to the n upstairs. 4 to the n over n factorial. That our guess is maybe this 4 to the n here is wearing the pants in the relationship. But let's look at some numerical evidence first. Let's compute the values of the first few ratios in this series. And the first few ratios, if we compute them out numerically, here they are. So the first ratio, the ratio of the second term to the first term, is equal to 2. And the one after that is 1 1/3, so 4/3. And then the next ratio is 1 because the third and fourth terms are equal to one another. And then the ratio is 0.8, 0.6, 0.5, etc. So our ratios start big and start decreasing. And of course our question is, how much do they decrease? What is the limit as n goes out to infinity of these ratios? So to find that, let's do the same thing we did before. Let's set up our ratio test with this particular sequence A sub n. So we need our sequence of ratios. And our sequence of ratios, rho sub n or r sub n, whatever you want to call it, is the ratio of the n plus first term to the nth term, with an absolute value that again doesn't matter because all of our terms are positive. Well, let's set this up and see what happens. Give myself some space here. So upstairs, a sub n plus 1 is 4 to the power n plus 1 divided by n plus 1 factorial, n plus 1 the quantity factorial. And downstairs, we get the nth term, 4 to the n over n factorial. So now here comes the part that is a little unfamiliar the first few times you do it, is that we need to simplify out this quotient before we take it to limit as n goes to infinity to figure out the asymptotic ratio. And again, when I simplify this fraction, I'm going to try to keep the pieces which are similar together. So my 4 to the n plus 1, which ends up in a numerator, I'm going to put that one together with the 4 to the n that it matches in the denominator. And then I've got my factorials, the n factorial, which ends up in the numerator, and the n plus 1 factorial, which ends up in the denominator. And now the task is to simplify out this quotient before we take the limit as n tends to infinity. Well, one of these factors is easy enough. We did an example like this a moment ago. How do we simplify 4 to the n plus 1 over 4 to the n? Yeah, we end up with a 4 upstairs. There's one extra 4 upstairs than there is downstairs. So that first factor simplifies to just 4. So let's write that one in. That one's the simple part. Now the fun part is figuring out what happens when I divide n factorial by n plus 1 factorial. Well, what does n factorial mean? What's the definition of n factorial? It's n multiplied by every whole number which is less than n. Sorry, every natural number which is less than n. So n times n minus 1 times n minus 2 times n minus 3 times dot, 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 all the way down to times 3 times 2 times 1. So that's the definition of what n factorial is. And if that's what n factorial is, then what's n plus 1 factorial? It starts with n plus 1. And what's the next factor? It's n. And then it's n minus 1. And then it's n minus 2. And it ends in the same place that n factorial ended, 3 times 2 times 1. This is what I always, as long as I work in mathematics, I still do this every time I have to simplify a quotient of factorials. I write it out like this. Because when you write it out like this, now we can see exactly what happens. What happens when I divide n factorial by n plus 1 factorial? I cancel a whole bunch of stuff. And that's the wonderful thing about the ratio of one factorial to another, is that usually when I divide a factorial by another factorial, I get a whole lot of canceling going on. And once all the dust has settled from that cancellation, I should be left with something really nice. I still have my 4 from out in front, but I also have, what's the only thing that survived that bloodbath of cancellation? N plus 1. Yep. And so really, the ratios of this sequence are 4 over n plus 1, which again, check it. When n is equal to 1, that ratio is 4 divided by 2, which is 2. When n is equal to 2, we get 4/3. Yep. When n is equal to 3, we get 4 divided by 4. Yep. And so on. So once all of the dust is settled with our factorial, we want to know what the asymptotic ratio of this series is. What do? Take the limit. Take the limit of those ratios as n goes out to infinity. And what do we get this time? What is the limit of 4 over n plus 1 as n tends to infinity? 0. As advertised. So the common ratio of our series is 0. So what does that tell me about my series? It converges. The sum of 4 to the n over n factorial converges. Again, because that ratio was less than 1. And another teaser for next week, even though we don't have to know this now, we can actually say what this series converges to. It converges to e to the 4th. Stick that in your pipe and smoke it. We'll talk more about why that is next week. But even though, to finish out this example and to get you in your groups, even though it looked in the beginning like this thing may have been a geometric series with a ratio of 4, which would have been bad news, because that ratio is bigger than 1, which would imply that this series should diverge. The n factorial in the denominator won the day. Right? The n factorial downstairs was going to infinity, right? Much faster than the 4 to the n upstairs was going to infinity. So the factorial was wearing the pants in this relationship. And even though we had something geometric upstairs, the factorial downstairs was ultimately what was important in this sequence. And the geometric asymptotic ratio was 0. Which means that this sequence, even though that 4 to the n is upstairs, still goes to 0 faster than any geometric series does, at a higher order than any geometric series does. So in our series, 4 to the n over n factorial belonged up here on the order thermometer, 4 to the n over n factorial. Even though that 4 to the n upstairs was a factor that looked like it was geometric, it is geometric, the presence of that n factorial actually relegated it to the factorial category, which is still convergent, because those terms go to 0 faster than any geometric series does.